So we now see that while we had a problem with three unknown stresses to be determined, and there were two equilibrium equations, we have now used the strain displacement relationship and seen that one more equation can be obtained by properly differentiating the strain displacement relationship. And now we get the third equation, which we say is the compatibility equation, which relates the strains epsilon x and epsilon y to the next strain, that is shear strain over here, which is the relationship delta 2 epsilon x by delta y square plus delta 2 epsilon y by delta x square is equal to delta 2 gamma xy by delta x delta y. Okay. Now we say that having obtained the compatibility condition, we now try to express that in terms of stresses, because our objective is to determine the stresses. So we have got from Hooke's law the relationship between strain and stress, simple relationship which we have derived from Hooke's law. Epsilon x is 1 upon E sigma x minus mu times sigma y and so on. So this I substitute in this compatibility condition, which involves epsilon x, epsilon y and gamma xy. So we now see that these three equations or these three quantities are now substituted. Thereby the compatibility condition is then expressed in terms of sigma x, sigma y and tau xy. So we are now substituting that. So this is for epsilon x, this is for epsilon y, and this is for gamma xy. Is that correct? So we have now got the relationship, the compatibility condition expressed in terms of the stresses itself. So we are now in a position to get or to deal with those three unknowns, sigma x, sigma y and tau xy, where we have got two equilibrium equation and the third, which is the compatibility condition, now expressed in terms of the stresses itself. Okay. Okay, so now I am summarizing the tools available to me. I have got the two equilibrium equations directly derived for the element and the compatibility condition, which is now simplified and got it in this particular fashion over. Okay, now I am trying to give different form to this. What I am doing is, earlier I have got that equation in this fashion, the compatibility condition. I am trying to get the same one from a slightly different angle. I will say that I have got these two equilibrium equations. Now if I differentiate the first equation twice with reference first with reference to x, the second one with reference to y, and add the two. So I am now getting this left hand side involving sigma x, delta sigma x by delta x square, delta sigma y by delta y square, and if we say that x and y, the forces which are applied over here. Now, yeah, perhaps I am sitting on your chair. So now I am saying that if the body forces x and y are not there, only the body is there subjected to, let us say, some other effect, then my x and y are not there, and I will be getting, by differentiating first equation by x, the second by y, then we will be getting the addition of the two equations resulting into this third equation. So I am differentiating this with reference to x, so that is first derivative. Second one with reference to y, that is the second term. While these two terms are added and taken on the other side, and then we are getting it as delta 2x by delta x delta y over here. So I think this is two times of that, not one times. It is two times. Is that correct? This should be 2 times. So I will now simplify. This should be 2 times. Is that correct? So I am getting the equation in this fashion. Okay. Now having obtained that, now I substitute this relationship, that is delta 2 tau xy by delta x delta y, in my compatibility condition which I have derived over here. So here I already got the derivative delta 2 tau xy upon delta x delta y. For that I make a substitution from this equation. So I have got this particular equation involving the second derivative of the shear stress, that I substitute in the compatibility condition and now get the simplified compatibility condition in this fashion. So I am now getting, when the body forces are only present and general forces, if they are also present, then my right hand side will involve the summation of these forces and their derivatives. So now I am saying that the compatibility conditions are obtained in terms of the stresses sigma x, sigma y, and of course the forces that you are applying delta x upon delta x and delta y upon delta y. So I will now say that my compatibility conditions are obtained in this particular fashion, and now I am summarizing the equations available to me. The first two are the equilibrium equations, where I will now say that if the force is applied, say I am taking the axis system xy, where y is my direction of gravity vertical, and if I say that if only the self weight is applied, weight of the body, where rho is the mass density, that is mass per unit volume, then I will take the force applied per unit volume as rho into g, which is the weight, and I will now say that my equilibrium equations, the first two equilibrium equations where only vertical load is applied, are these two, and the compatibility condition is now the third one. So there is no other force applied. The force that I am applying rho g is constant with reference to x and y, so its derivative will be all 0. So I am now getting the condition to solve, or the equations to solve the plane stress problem over here. So I am having two equilibrium equations and one compatibility condition, all expressed in terms of the basic unknowns sigma x, sigma y, and tau xy. Okay. Now we say that to solve this particular type of problem, which are nothing but the partial differential equations. Please remember, now you are dealing with partial differential equations with constant coefficients. There are various methods of solving that. I think you have got one subject in the present semester, numerical methods. So those are the class of, you can say, methods available for solving different types of equations. Now we are having partial differential equations, and to solve that there is one method available, which is the method of substitution, and this method involves combining these three equations and converting that into a single equation over here, and then solving that single equation in different situations over here. So what we do is we make a simple substitution for stresses. The stress sigma x, sigma y, and tau xy, now we say are the forces of the stresses within the body. The body itself is in xy plane, so the stresses will vary within the body. So I will say that I will select a function phi, which is a function of x and y, and if I take a function in this fashion, that is sigma x equal to delta 2 phi by delta y square minus rho g y, that is a substitution I want to make, where phi is some function of x and y. Please remember, phi is some polynomial function. It may involve x square, x cube, any power of x, and so on. So if I take phi as some function of x and make this substitution, delta 2 phi by delta y square minus rho g y, that is for sigma x. sigma y delta 2 phi by delta x square minus rho g y, and tau xy is delta 2 phi by delta x delta. Suppose I do that and then substitute that in the compatibility condition that I have got. So I have got this compatibility condition. I have got in fact these three equations. In the three equations, I substitute for sigma x, sigma y, tau xy, simplify that, and thereby I will be able to get this fourth order partial differential equation delta 4 phi by delta x4 plus 2 times delta 4 phi by delta x square delta y square and so on. So what I am doing is I have got these three substitutions. So I substitute that in terms of compatibility conditions, and then the compatibility condition which is now obtained as an equation, fourth order partial differential equation with constant coefficient. That is only, it has got the middle term with a constant coefficient 2, others have no coefficient. So now we say that we have started with first order partial differential equation and now finally got a fourth order partial differential equation. Similar equation later on in the next semester when you study problem of plates, there you will see that you will be left with the I think